Okay. Okay. Yeah. So we also tested. We also had another test setup where we used entire domains as a positive set, and then took a max score as a number, and it helped the most to the ESM2 base model. Then we checked how fungal motifs can be distinguished from random fragments, and we can see that there was also a huge improvement. And most striking for me was this last result. It seems that BLSTM has learned on bacterial sequences how to use ESM2 embeddings to detect amyloid signaling motifs, and was able to translate this knowledge to detect fungal motifs. Okay, but how does it translate to our final end goal to be able to detect ASM amyloidic signaling motifs in entire genomes? So here's an example. We tested. Sorry for this slide. First, we tested Proteome-BERT. We used Fusarium xysporium proteome because it has the largest number of previously annotated amyloid signaling motifs. Okay, and these are the ones here in the top, the red points. And we predicted motifs using Proteome-BERT, and it was able to detect around more than 50% of, with default cutoff, more than 50% of motifs. And we have precision of maybe roughly 0.2, maybe not so impressive, but still very useful. And last but not least, we found a very brand new motif, amyloid signaling motif family. So we're quite happy with this result. But then we tested the ESM2 based BLSTM, and it really was something which impressed me, because now you can see we found like 80 or 90% of ESM in this proteome with precision around 60%. So for me it's great. It means that the motif is that the method is finally capable of what we want to do. So this we have to check it with other proteomes, because this is a very recent result from last days, but it looks very, very, very promising. Okay, how much time do I have? Fine. Okay, so few more insights as I still have some time. So Proteome-BERT embeddings representations have their own merit. It seems that they quite nicely separates amyloid motifs in the embedding space from other non-amyloidogenic proteins. Even if some, well, you can't probably see it, but even if some motifs had a low score from the model, it were in the right place. This is quite opposite to ESM2 based BLSTM, where some high scoring motifs are kind of intermixed with non-amyloidogenic motifs. We can also see that Proteome-BERT was quite good in generalizing from bacterial effector sequences to bacterial receptor sequences, and from bacterial effector sequences to fungal effector sequences, but was quite bad with fungal receptor sequences, so the most different ones, yes. And here the detection rate was similar to non-signaling amyloids. And this was ameliorated with ESM2 BLSTM. ESM2 BLSTM was also much more consistent when we looked at how they detected motifs from subfamilies. You can see it here. But we quite liked how Proteome-BERT used embedding space to capture these families, because, for example, these two families, BUS3 from bacteria and PP from fungi, are related, and they come together in embedding space. To conclude, it seems that we have two reasonable, quite well models capable of scanning entire proteomes, and this is especially true for ESM2-based BLSTM. They can do some out-of-distribution searches, which was important for us. And maybe the one fly in ointment is that, well, it's still not lightning fast. If on personal computer, on a good personal computer, it takes like dozens of hours for scanning one proteome, but just maybe technical thing. Finally, I would like to thank the first authors of this work, Jakub Gałązka and Krzysztof Pysz, and thank you for your attention.
Wonderful. Thank you so much. We have like a few minutes for questions. Are there any? Okay, so I will go ahead with one question. I was wondering, like, when you show like the precision that you got like from your Motifs-Seq, do you also have like an idea of what like recall look like?
Yes. So definitely. So this is okay. I didn't prepare a slide on it, probably. Let me think for a moment. So in fact, here you have, we call it retention on this slide, but this is recall in principle. Okay, so these are recall values for default threshold. Okay, this is for default threshold, and for default threshold, we may had worse precision, but this is more or less how it looks like. Yes, so the best model with default threshold easily gets finds like 70, 80, 90% of motifs. And by the way, this precision here, where I have it, this precision here, this is the average precision. So it means this is this average precision over value of recall. Yeah. So I think it approximates area under recall precision curve. So just to clarify.
Wonderful. Are there any other questions? Okay, if not, we can thank the speaker again. And I guess I forgot to mention before that Witold was also like the first of our proceeding presentations, right? So the paper should be out soon, and you can read like more details.
I think it already is.
Perfect. So if you want to see more details, I guess you can see it online.